Thanks for the invitation, Boumediene. So I'm very pleased to be here. So I'm new to dynamical systems. I really started a couple of years ago and studied them. They are very interesting stuff. And I remember we met 10 years ago, and Boumediene was telling me about this coupon operator, but I didn't pay much attention. And now, there's a lot of interest, right? So I will discuss a little bit our results, if this works. See? Okay. So I will discuss results about how the problem of statistical learning, these operators. In particular, I will focus on stochastic dynamical systems. So discrete stochastic dynamical system, I will discuss how to learn the transfer operator. And I will try to put this problem on a statistical footing, so discuss what is the notion of loss function, risk, and discuss new learning algorithms, recent learning algorithms, in particular this reduced rank regression algorithm. And then I will discuss bounds, learning bounds for this operator, in particular focusing, like in the last talk, about spectral bounds. So we're interested in finding the eigenfunction and eigenvalues. Then in the second part of the talk, if there is time, I will discuss about learning continuous system, in particular learning the generation of stochastic diffusion systems. Okay. So, so here is some of the notation. So we have, let's see if, no, doesn't work. So, okay, xt is our time homogeneous Markov process, and then the forward transfer operator is defined as the conditional expectation of a value of a function and observable tomorrow, given the value of the state today. So it's a conditional expectation. And as you see, it is defined on some space F, mysterious space F here, which we need to choose so that the operator is well defined. So the range of the operator needs to be the space itself. So, and this is a delicate business, okay? So for instance, if the space is finite dimensional, right, and it is, so if I know that this finite set of functions form an invariant subspace, then the operator is identified by this matrix G, which evolves function coefficients, okay? Interrupt anytime if you have questions. So we will consider throughout the talk stochastic dynamical systems which have an invariant distribution. Okay, so they are defined here. So this, is there a pointer, maybe a stick which I can use or something? Okay, I will just stretch my arm. So let's see. Maybe. I don't think that's a, no, no. Okay, so, never mind. Okay.
But it's not a pointer.
That is good. So this is the transition kernel. Okay. So this is my transition kernel. Okay. And pi is the invariant distribution, an invariant distribution. Okay. So in this case, it is not difficult to see that the operator is well defined on the space of square integrable function with respect to pi. Okay. And so the operator is bounded, the norm is less or equal than 1. So the challenge that we're addressing is to learn this operator, and this is a challenge from, say, machine learning, statistical machine learning perspective, because if you know about, say, supervised learning, let's say, so learning a regression function from data, you don't know the function and you want to learn the function. So here, we don't know the operator, and also we don't know its domain. So we will have to choose a domain of the operator, okay? It will not be the whole space. We need to have, choose our domain of the operator. Okay, so how do we do that? So first, there's some related work on, so of course, there has been a lot of work on data-driven algorithms for learning dynamical systems, which have inspired us. Also, some very interesting work in computational physics, in particular. So we've been motivated by work by my colleague Michele Parinello, who's working in molecular dynamics. And also in machine learning, there has been some work for quite a few years on these conditional mean embeddings and also vector value learning. And some of the algorithms that we use are intimately related to this research. Okay, so what is the approach? So the approach is, so we work with reproducing kernel Hilbert space in part of the talk. So the approach is to choose this space H, which is reproducing kernel Hilbert space, is nothing fancy, so you can just think of it as the span of a finite set of basis functions, but it could actually be a richer space, so say subbolus space or something like that, so it can be infinite dimensional. And then what we do, we learn from data. I still haven't mentioned what the data is, but we will learn an operator on this space, okay? Okay, we don't know the invariant distribution, so this is our working space. This is reproducing kernel Hilbert space, okay? Now, going back to the previous equation, right, so if the transfer or coupon operator, right, is approximately equal to this, then you can see that what we are looking for is for the operator G, such that is a joint acting on this set of basis functions models the conditional expectation. Okay, and so then if we have a data sequence, a trajectory, let's say, of points, then the idea is to embed the state in the Hilbert space, and then this will be our loss function. So we try to, so looking at this equation, so we try to mimic this equation. We try to predict the next embedding as a linear operator of the current embedding of the state. Okay. Then we simply take the expectation of this loss function over my trajectory, and so this is the same as taking the expectation of the joint distribution of the initial state from the invariant distribution and the future state y, and this is our notion of so-called risk function. Okay, so we like to find an operator G which minimizes this risk function. Okay, so so we need to define. We need to choose the space H. It's very delicate business. At the moment, it is fixed. Say I know what a good space is, and then I want to minimize this. I want to find the minimizer of this risk function or risk functional over operators on H. Okay. So these kind of parallels. So, for instance, if you have read the paper by Cooker and Smale of Mathematical Foundations of Learning, so if you read that paper, there it is described for learning regression functions, so real value functions. So here we are learning an operator instead. Okay. So how do we find how do we minimize this risk? So standard in statistical learning, we don't know the underlying distributions. We only have data, right? So we have, so let's say we have a trajectory of the system in a stationary regime, and then we observe a trajectory of endpoints, and then we construct this empirical version of the risk, which is called empirical risk, and we try to minimize the empirical risk over operators in the space. We also add some regularization, right? This is a standard idea to somewhat penalize two complex operators. And here we had the Hilbert-Smith norm of the operators. Okay, you could add some other regularization term. Okay, so this is a very simple idea. And then you have different algorithms or different estimators which within this general class of empirical risk minimization estimators. So of course there is kernel ridge regression, which is a very famous estimator, which is exactly this, minimize this over G. Okay. Then there is principal component regression, which is similar to DMD and this extended DMD. So the way it works, it chooses a fixed set of basis functions which might be computed by finding the leading eigenfunction of the covariance matrix of these features. And then it does, it minimizes the empirical risk over these basis functions. And then we have this estimator that we have introduced recently, so a couple of years ago, which we call reduced rank regression estimator, which minimizes the regularized empirical risk with an additional rank constraint. Okay, so we additionally say that the rank of our estimator should be less or equal than R. Okay. If we don't add the rank constraint, in any case, since we have finite number of data points, the estimator will be of rank at most n. Okay, so n is the sample size. And also you can do some, say, a simple linear algebra, and you can see what the form of the solution is. So the solution, the G hat is the minimizer of this, either with the rank constraint or even with the PCR. And then the estimator is, the solution is identified by this n times n matrix, okay, of coefficients. Okay. Also in our paper, you also see how to compute the spectral decomposition of the estimator so how you can reduce the computation of the negative decomposition of the estimator of the G hat to the negative decomposition of a matrix. Okay, so let us skip that. Okay, so what I want to discuss next is how good is this estimator? Okay, so what does it mean that we estimate well the underlying transfer operator, and what about eigenfunction and eigenvalues? Okay, so this is a very interesting problem, and it kind of so for people working in statistical learning, it's kind of a new problem because people in the past have worked mainly with estimating operators with respect to the Hilbert-Smith norm, okay, and that's what people cared about. So here we need to pay attention to two quantities, okay. So the first is, since we also care about eigenvalues and eigenfunction, is this metric, what we call this metric distortion. So it is the ratio between the value of a function in my Hilbert space, my reproducing kernel Hilbert space, the relation of the norm in the space to the norm in the, say, ambient space L2 pi. So typically this H will be an eigenfunction of my estimator. And the second quantity I need to pay attention is not the Hilbert-Smith norm, but rather is the operator norm, okay, which here I define explicitly. Okay. So both quantities, so this metric distortion and the operator norm error, enter into spectral bounds. Okay. And the way you see that is that, so if you assume that H hat is an eigenfunction of the estimated operator, then you see that H hat is an approximate, so it's eigenfunction of the transfer operator, so you like this to be 0, right? So this quantity is small if both metric distortion and the operator norm, what we call it estimation error, or the operator norm error, are small, okay? So it is not enough to have small estimation error, you also need to control this metric distortion. In addition, it is also important to control the rank of the estimator, because you can show that if the estimator has high rank, then metric distortion can deteriorate, and then you don't estimate well the spectrum. Okay, so that's why we like to introduce this rank constraint. Okay. So briefly, I want to tell you a little bit about how we bound these quantities. So the metric distortion is to control metric distortion, you need to look at the covariance operator, right? So the covariance operator is the expectation of the outer product of the this feature mapping itself, and okay, and the estimation error, we to bound it, we do an error decomposition in which we see different the interplay between approximation error and estimation error or estimation variance. So here, so we have the first term here is the distance between the projection of the transfer operator on the space. So this a pi h, right? It is defined here, right? We apply the transfer operator, then you project on h. Okay. So here you see that this quantity is 0 if the reproducing kernel of space is dense in the space of square integrable function. So this is typically a not standard, but say mainstream assumption which is made in statistical learning theory. So this first term we discarded in our analysis. Okay. But then later in the talk, or in Pietro's talk, you will see how do we choose the features, how do we choose the kernel. When we work with finite number of features, with neural networks, we need to pay attention to this term. Okay? So this is not, so this is for the next talk. And then you have these two other terms. The first is the estimation bias, which to analyze it, you further need to decompose it and optimize it over the regularization parameter and over the rank parameter. And then the last term is the only term which is purely statistical. Okay, so it's the term that you bound with concentration inequalities. Okay. So our bounds are depends on two parameters. Okay, so the first parameter is what is called the effective dimension, and it is a parameter which depends on our Hilbert space and on the invariant distribution, and it measures the rate of decay of the spectral decay of the covariance operator. And the second parameter, this parameter alpha, measures the size of the image of the restriction of the transfer operator in L2. Okay, so the case of alpha equal to 1 corresponds to the so-called well-specified case. So this is the case in which you know that the reproducing kernel of space is an invariant subspace. Okay, and actually all these cases correspond to the well-specified case with different level of so this different level of smoothness, if you want. So these are the bounds for reduced rank regression. So you have here the bound on the operator on the estimation error. And you see here that the estimation error, so the operator norm error, is bounded by the r+1 singular value of the restriction plus a term which goes to 0 in n, right? And how it goes to 0 in n depends on these two parameters, alpha and beta, okay? Okay, so the smaller beta, the slower the rate, and the larger alpha, the better the rate. Okay, so if alpha is equal to 1 and beta is say close to 0, this is the so-called parametric rate in statistics, which is order of 1 over square root of n. And here, importantly, you see the rates for the eigenvalues. Okay, and here you see, interestingly, that the rates contain. So there is a term which goes to 0, like for the estimation error, and then you have a term which might not be 0 unless the operator is finite rank. This we call spectral bias, right? So here, crucially, the spectral bias depends on the operator. So, okay, so if the operator has rank R, this bias term is 0, and I can estimate arbitrarily where the eigenvalues in that case. Okay. In contrast, for this principal component regression, I don't have these results. Okay, so because so the term here and the term here depend on the covariance operator, which it is not of finite rank. Okay, so the long story short is that if I have finite rank operators with this reduced rank regression estimator, I can estimate, I have a consistent estimator of the eigenvalues, and shortly you will see about the eigenfunctions. But for this principal component regression estimator, which, as far as we understand, is was the mainstream method in the field, you don't have this property. So you might have spurious eigenvalues. Okay? Then these results we can also extend to eigenfunctions. And so here you see that you have the spectral gap. So if you have the ith eigenfunction, and if the spectral gap is not too small, then when the eigenvalue bound kicks in, I have consistent estimation of the eigenfunctions. And so here you see this method, this estimator, in action on this quadruple well potential. So this is a discretization of the Langevin equation. And here you see the so black are the ground truth eigenfunctions. So the first is a constant function, of course, and then you have the next three eigenfunctions. And here you see that in orange is this reduced rank regression estimator. It does a good job at estimating eigenfunctions, whereas the principal component regression is it doesn't perform as well. Okay. Okay. So so let me move on. Maybe I don't know how much time do I have. 5 minutes. So I mostly skip this part. So we have some standard results for continuous system for stochastic diffusion processes. So here what we are interested in, so it is more practical to learn the infinitesimal generator of the process, which is defined here, right, as so the limit, right, of the transfer operators. And so the infinitesimal generator is linked to the transfer operator time step t by these equations. So since we are interested in finding the eigenfunction of the process, so the two operators have the same eigenfunctions. So what we have done in this more recent work, we have designed algorithms, estimators, which sample the process not necessarily at equally spaced time, so we don't need the notion of time lag. And we learn this operator L, or more precisely, we learn the resolvant of L, and we want to exploit prior knowledge about the underlying equation. So here, unlike the estimators for the transfer operator, which are purely or almost data-driven, so we just use information that we have time homogeneous process. Here we use the equation, the underlying equations to form our estimator. So I don't have time to go in detail to the details. So here in the talk it is illustrated for Langevin, for the Langevin equation. And so we use partial knowledge, in fact, in this work about the equation. So we use knowledge of the temperature, but not the potential. And then we learn the resolvant. And the approach, apart from learning the resolvant and using prior information, is similar to the previous approach. So I choose a working space, or my reproducing kernel Hilbert space, and then however, I modify the norm. So instead of measuring norms with respect to L to pi, I measure it with respect to this space W, which is a kind of subbolus space where the square norm is defined, right? So the square norm, so mu is some parameter, and beta is the inverse temperature of the process. So, okay, so I think, so maybe this part I'm going to quickly, but we can define again the notion of risk, and then we can define, so the trick is to adapt to the geometry of the space, right, so the space W, and then I have this notion of risk, and then I can naturally have an empirical risk minimization in which, so this is illustrated for finite number of basis functions, but it also works with, in general, reproducing kernel hyperspaces. So I need to estimate these two matrices, right? So this is the covariance like before, and this is some other covariance which adapts to the geometry. So there is, here, there is the infinitesimal generator there, and using my partial knowledge, I know its expression, so I need also to take the gradient of the features. Okay. So we do all these, and it works better than the transfer operator because we have put prior knowledge. And then what is in, so we can give spectral bounds like before, so the analysis is similar. I'll skip these. And then we can also, this is very interesting, this is more specific to Langevin dynamics, we can also learn from biased trajectories. So the problem is that these processes mix very slowly, so you need very long trajectory, something I didn't discuss through the talk. So we don't have IID data, we have a trajectory. In addition, we explore the space very slowly, and there are some methods from people working on molecular dynamics for how to accelerate the exploration of the space, and here we have adapted these estimators to these accelerated dynamics, and so we have a way to learn faster for these processes. I'm going to skip these. Then we have also, briefly to mention, large-scale kernel methods for the estimators. And then we have some recent work on learning distribution forecasting and long-term forecasting. So we have some bounds for these geometric ergodic processes where our forecasting error doesn't degrade with time. So we have uniform bounds, uniform forecasting bounds in times, which is quite interesting. And then, as you see the next talk, we have some work on learning the kernel or learn the representation. So, okay, so thanks very much.
Thank you very much.